something incorrect at the end of lecture A here. I said that the cyclic subgroup generated by A is a subgroup of G by definition. It really wasn't a definition for us. It was a theorem with the one or two step subgroup test. Defining this to be the set of all powers of A, first of all. You can say it's true by definition if you define it differently. If you define this to be the smallest subgroup of G containing A, then by definition you're saying it is a subgroup. And those two things are actually equivalent to each other. But by the way we did it, it does take proof that it's a subgroup of G, but we already did prove it. So showing it's a subset of H is also enough to show it's a subgroup of H. All right, we're going to make use of this lemma now. In thinking about this equality here, so we are again supposing that A has order n. And we're thinking about showing that the cyclic subgroup generated by A to the k, where k is an arbitrary positive integer, k is in, you could call it z plus, meaning arbitrary positive integer, that's pretty standard notation, equals A to the d, let's call it, where d is the GCD of n and k. GCD, I wonder if we're going to need the GCD as a linear combination theorem. We may. In fact, we will, but not for both directions. So our first proof is we're going to show that the cyclic subgroup generated by A to the k is a subset of the cyclic subgroup generated by A to the d. Again, these are definitely subgroups of the whole group. We have proved that. So we can just focus on the subset issue. Are they both subsets of each other? And there, we're just going to use the fact that d is a divisor of k. And the lemma. How are we going to use this lemma? It's to show that the cyclic subgroup generated by an element is a subset and a subgroup of some other subgroup. It suffices to show that the element itself is in H. In this thing over here, A to the k is playing the role of A over there, and this subgroup is playing the role of H over there. So all I have to do here is to show that really A to the k is an element of this. And that's based on the fact that D is a divisor of k. D equals GCD of n and k implies there exists, say, m, such that k equals m times d. Therefore, A to the k is A to the m times d is, using properties of exponents, A to the d to the m, which by definition is an element of this. Therefore, by the lemma now implies that the cyclic subgroup generated by A to the k is a subset of the cyclic subgroup generated by A to the d. It also would be a subgroup because we already know it's a subgroup of the whole group. Next, we show the other inclusion. You can write it backwards, subset. Symbols like that if you like. You already have, but it's okay. We once again want to use the lemma to show this. What we really need to do is we need to show that A to the d is a power of A to the k. It's in here. And for that, you need the GCD as the linear combination theorem. GCD is linear combo theorem. Implies there exists S and T integers such that D, the GCD of n and k, is a linear combination of n and k. It's ns plus kt. Again, we want to show a to the d is in that cyclic group. It is a power of a to the k. Go ahead and try raising it to the d and using this factor and see what happens. Using a property of exponents, we can write this. Now probably we need our assumptions. We are still assuming that the order of a is n. And I see an a to the ns there. I bet that turns into an e. Yes, it does. Oops, not there though. What about that one? So this is going to be e to the s, which is e. What about a to the kt? And what's my goal? My goal is to show that a to the d is a power of a to the k. That seems pretty good then. A to the kt is a power of a to the k. I can just keep writing that here. This equals a to the k to the t power. This is then an element of the cyclic subgroup generated by a to the k. And that does it. That means a to the d is in there, which means, by the lemma, that the cyclic subgroup generated by a to the d is a subset and also a subgroup of this. The two inclusions together then mean you have equality. Okay, is it okay if I don't finish writing it? You should say, therefore, by the lemma over there, this is true, and therefore they're equal. There are corollaries of this. In a finite cyclic group, the order of an element divides the order of the group. Because of this equality here, actually. A to the k is an arbitrary element of a finite cyclic group. N is the order of the group, because it's the order of the subgroup of a generator. But it's the order of the generator. The fact that the order of a to the k is this fraction means, if you multiply both sides by the GCD, that the order of a to the k does divide in. This is going to be an integer here. The order of any element has to be an integer. So because you have equality, this is going to be an integer, and therefore you can multiply both sides by the GCD to get that thing. This thing, the order of a to the k, divides n. This fact generalizes to any finite group, cyclic or not, though the proof is more difficult for non-cyclic groups. We'll talk about it in chapter 7. Suppose the order of a is n, then the cyclic subgroup generated by a to the I and a to the j are the same if and only if the GCD of those things with n is the same. And also, a to the j is going to be a generator of the cyclic subgroup generated by a if and only if the GCD of n and j is 1, if and only if they're relatively prime. I'll let you write that down if you want. There's also the fundamental theorem for cyclic groups, which I'm not going to take the time to go over on the slide. It is very important. It's called the fundamental theorem of cyclic groups. I can quickly verbally say it, what it says. One thing it says is that if you've got a cyclic group, all of its subgroups are also cyclic. If it's a finite cyclic group, say of order 24, like in the quiz, right? Well, G was a group, cyclic group of order 24 on the quiz. It's got one subgroup of each order which divides 24. For each integer, for each positive integer that divides 24, there's going to be one cyclic subgroup for that divisor. Divisors of 24 are 1, 2, 3, 4, 6, 8, 12, and 24. 1, 2, 3, 4, 5, 6, 7, 8 divisors of 24. The cyclic group of order 24 has 8 subgroups, including the trivial subgroup of order 1 and the non-proper subgroup, the entire group of order 24. You would have 6 non-trivial proper subgroups of orders 2, 3, 4, 6, 8, and 12. that is a brief summary of what the fundamental theorem of cyclic groups says. It says a little bit more than what I said, but you can look it up. A few more things that I want to talk about here before we end today is I want to talk about the idea of a subgroup lattice. Maybe we can do it for Z24 actually. Well, let's again say let's do it in the abstract. We have an element of order 24, and G is the group generated by that element, so it's going to have order 24 as well. What a subgroup lattice is it's a diagram showing you how the subgroups of the given group fit together. Subgroup lattice. You put the whole group up top. Underneath, you put subgroups, proper subgroups. And if you've got a certain proper subgroup that also has other proper subgroups of it, you put those underneath that intermediate one. This has order 24. There is a cyclic subgroup of order 12. What would be a generator of a cyclic subgroup of order 12? That would be for Z24. A to the second power, yeah. A to the second power, cyclic subgroup generated by A to the second power has order 12, right? It would include E, A squared, A to the fourth, A to the sixth, A to the eighth, A to the 10th, up through A to the 22nd. A to the 24th would be back to E. That would have 12 elements. There's going to be one that has 8 elements. Generator would be A cubed. Would it be a subgroup of the cyclic subgroup generated by A squared? No, it would not include A squared, for example. Put the lines underneath. These are both subgroups of G, but they are not subgroups of each other. There's a cyclic subgroup of order 6. Generator would be A to the fourth. Cyclic subgroup generated by A to the fourth would consist of these elements. And that is a subgroup of the cyclic subgroup generated by A squared. A squared also contains those elements plus more. It's not necessarily clear where to put these things horizontally speaking. But I can certainly write that. Is it a subgroup of that? No. It doesn't contain A cubed. Cyclic subgroup of order 4 is going to be generated by A to the 6th. Is that the camera? Okay. All right. That's a subgroup of that one. It's not a subgroup of that one. It doesn't have A to the fourth, for example. Cyclic subgroup of order 3 is going to be generated by A to the 8th. It's a subgroup of this one, not a subgroup of that one. And the one of order 2 is going to be generated by A to the 12th. Contain A to the 12th, just like these two do. It's going to be subgroups of both of these. Do notice that both 4 and 6 divide 12. It's no accident. Do notice 2 divides 4, it also divides 8, it also divides 12. 3 divides 6, it also divides 12. Then there's the trivial group down here. Altogether giving us 8 subgroups of the cyclic group of order 24.
Isn't
Am I missing one?
well, isn't A6 a subgroup of A2? Or like those, the cyclic subgroup
Yeah,
generated by
yep,
A6?
You're right, thanks.
Yeah.
I missed that one. So yeah, it's sometimes tricky to know whether you're completely done or not. So somehow this subgroup lattice maybe tells us a lot of information about a group, and in particular, if you've got two groups and you're wondering whether they are isomorphic or not, I mentioned that word before, essentially the same with regard to, say, their Cayley tables when you put the elements in certain orders, maybe their subgroup lattices should have the same structure too. So if they had different structures, then they would not be isomorphic. Remember, we are mathematical taxonomists, right? We're trying to see all these different examples and trying to classify and organize things to understand how everything goes together here. There is stuff, again, about the Euler phi function, which is great. And it's definitely something you should remember. I do want to get onto something else here, though. Again, phi of a positive integer d is the number of positive integers less than d that are relatively prime to d. This says if d is a divisor of n, then the number of elements of order d in a cyclic group of order n is the Euler phi function applied to d. The authors make an important point, or the author makes an important point about this. It's not really dependent, well, as long as d divides n, the number of elements in a cyclic group of a given order doesn't really depend on n, as long as d divides it. So for example, 10 divides 100, it also divides 1,000, it also divides, of course, 10,000, 1,000,000. Phi of 10 is 4. In each of the groups Z100, Z1000, and Z1,000,000, there are exactly 4 elements of order 10 in every one of those groups. So as long as n as d is 10 in this case, divides n, and doing different n's here, then this answer doesn't depend on n. It only depends on d. The elements of order 10 in Z100 would include 10, 30, 50, 70. Those have order 10. I'm doing addition, mod 100 there. Elements of order 10 in Z1000 include 100, 300, 500, and 700. Elements of order 10 in Z1,000,000 would include 100,000, 300,000, 500,000, and 700,000. And those would be the only elements of order 10. So that's worth remembering. In a finite group, the number of elements of order d is a multiple of phi of d, whether that group is cyclic or not. And there is a formula, so to speak, for phi of d in the book. I'll let you look that up. Maybe I'll talk about it more on Wednesday. All right, we've got about 9 minutes left. In those 9 minutes, I'd like to start the next chapter. Start talking about what are called permutation groups. And this is more complicated than cyclic groups. But at the same time, if you're going to have fun in this course, this may be the chapter to have fun in. It depends on your taste. I think even though permutation groups are more complicated to think about, I think they're really fun. In fact, I've grown to like them more and more over time. What are they? They are groups whose elements are functions and whose operation is composition, but not just any old function. It's typically a function defined, well, okay, it's a function from a set to itself. we're given an arbitrary set, call it capital A, not necessarily a group. A can be any set you want, pretty much. Except the empty set. You wouldn't really want the empty set. A is not empty. A permutation of A is a function, call it alpha say, from A to itself. That is 1 to 1 and on to. And you know that that means it automatically has an inverse function. A group of permutations on a set A is a set of permutations on A so a collection of functions on A that are from A to itself that are 1 to 1 and on to, that forms a group under function composition. Function composition is the group operation. In particular, the main thing you got to verify, main things are closure, the identity being in there, and inverses of every element being in there. Associativity is going to follow automatically because function composition is definitely associative. The most common thing that we use for capital A is a finite set. Now that finite set could be a collection of any objects you want. Could be a collection of people, could be a collection of colors. We typically take it to be a collection of numbers. The first n positive integers. Typically, we take A to be the set of the first n positive integers. But we're not thinking of A as being a group. This A itself is not a group. It's just a set. We could make it a group if we added a 0 to it and did, say, addition mod n plus 1. But, or if we were doing addition mod n and we thought of n as being 0. But we're not doing that. So it's just a set. And we define S sub n to be the set of all permutations of this A. Maybe I should call it, okay, no, I don't want to call it A sub n, because that's reserved for something else. Under function composition. Set of all permutations of A under function composition. That will form a group. And this group's got a name. It's called the symmetric group. On n objects. It's often represented as either an array, a matrix, or as a composition of what are called cycles. And I think for today, for sake of time, we'll just talk about the array form. If you're given an element, say, of S7, what does that mean? It means alpha is a function from this set to itself, where n is 7, that is 1 to 1 and on to. So alpha is a function How could that function be described? You could try coming up with some sort of formula, but maybe not. That sounds not really doable, perhaps. Another way you can represent this function is with this array notation. What you do is you make a matrix, you put all the inputs in the top row of the matrix. Those are going to be the inputs of alpha that go into alpha, and the corresponding outputs go right underneath. So when you plug in 1 into alpha, you could, for example, get a 5. And when you plug in 2 into alpha, you could get, for example, a 3. You plug 3 in, you could get 7. You plug 4 in, you could get 4. You plug 5 in, you could get 1. I got to be careful here. This is a one-to-one and onto function, so I do not want to repeat a number down here. And all numbers should be included. I have not used 2 or 6 yet. Those are the ones that I want to include down over here. I picked them in a somewhat arbitrary order. This is just one example. How many elements, how many functions are going to be in S7? Well, since I picked the numbers in a somewhat random order, I really had 7 choices for the first number that I put there as the output of alpha at 1. I could also write this, alpha of 1 is 5. I already picked one number there before going on to the next one. I had 6 choices left there. Then 5, then 4, then 3, then 2, then 1 choice left at the end. All together giving me 7 factorial possible permutations. Now you see the relationship to discrete math. 7 factorial possible permutations in S7. The order of S7 is 7 factorial. In general, the order of Sn is going to be n factorial. Well, let's see, 5 factorial 120. What is this, 5040? That's not right to people. Or is it 4,000? I think it's 5,040. Does that sound right? Anybody want to refute that for sure? I think that's right. 5 factorial is 120. 6 factorial is 720 times 7. Yeah, okay, that's right. This has got 5,040 elements in it. Yikes. All right, see you on Wednesday.